Okay. For the last 2-3 classes, we have been learning how to obtain the first order differential equation. So, before going to the electrical circuits specifically, let me give you some problems that you solve before coming to the next week's classes. Firstly, all the problems that you have done using the Lagrangian method, where you have obtained the second order equations, you obtain the first order equations for them. So, that is the thing to be done, but in that assignment do not do the whole problem all over again, because you have already drawn the physical system diagram, obtain the kinetic energy, the potential energy, the Lagrangian, all that remains. So, in this assignment what you do for those problems, you just start from there and then do the rest of the steps to obtain the first order equations. Okay. In addition to that, I will give you some problems which you solve a priori from first principles to obtain the first order equations. The first problem will consist of a mass which will be standing on a spring damper support on the ground, and if you apply a force, that will move up and down depending on the force. Okay. But that is not the complete story. There is a lever, and at the other end of it there is a mass hanging by a spring. So, there are two masses M1 and M2. There is the spring constant K1 and there is another K2, there is one R, and there I have to also specify the ratio A and B. For the sake of simplicity, assume that this rod will remain close to horizontal position, so that you do not really need to consider these angles. That approximation you assume and go ahead. So, in this case there are two masses, and therefore, there will be two momentum coordinates and two position coordinates, 4-dimensional system really, and then the rest will be simple. Is it simple? Okay, you do it. Fine. So, that is 1. 2, I will give one electrical circuit to be done using this method. There is a voltage source connected with a resistance and a capacitance, and then an inductor, then again an inductor, and then again a capacitance. I would like to add something more. Yes, fine. So, L1, L2, C1, C2, R1, R2 and E. For this, obtain the first order differential equations. Note it down. Suppose there is a cart like thing which is able to move on the ground, okay, and this fellow has some mass, say M1, and it is being pulled by a force F, and on this surface there is a friction, that is say R1, viscous friction, but here is a mass that is connected by means of a spring. So, that is another mass m2. And here is the k spring constant. I suppose that completes the story. No, there will be some kind of a friction. So, how many degrees of freedom does it have? 2 position coordinates and 2 momentum coordinates. Because now we are talking in terms of the first order equations. When we do so, we will have to talk in terms of both position as well as the momentum coordinates. Okay. We have already done the problem in the class for the inverted pendulum, right? Obtain the first order equations for that. So, I am not again writing it. We have already done the problem, but we did it following the Lagrangian method. So, obtain the first order equation for that. So, that is problem number 4. So, I will write problem number 5 here. Here this problem will concern the way the loudspeakers work. So, how does the loudspeaker work? It is a electromechanical system, right? A loudspeaker is a electromechanical system. There is a magnet which is energized and that pulls a diaphragm which oscillates. The diaphragm pulling and other stuff, that is a mechanical system. The other thing is the electrical system, and in between there is a coupling through magnetism, which is similar to the DC machine problem that we did. So, remember that. So, you have some kind of a voltage source. So, that is E t, the signal which you want to be reproduced in sound. A resistance and inductance will be there, because there is a winding will always have these things, and then you imagine that you apply this to these 2 terminals, and here there is some kind of a transducer that applies that pulls it with a force F. Okay. Here is an iron piece, here is an iron piece. I am just schematically drawing, it should not be like that, but nevertheless you understand that here is something that converts the current signal into a force signal to be applied on the mechanical side. What is there in the mechanical side? There must be some kind of a mass which is essentially representing the mechanical arrangement of the loudspeaker. So, you get the sound here, fine. But not only that, this fellow should not be hanging in the air, that has to be attached to some kind of a ground by means of a spring damper arrangement, right. So, this is the mechanical ground, and this arrangement is connected to the mechanical ground by means of the spring damper arrangement, and then as this force is applied, it will oscillate, it will vibrate, and that is what is communicated into the air. So, there will be a mass here m, there is a spring constant k, there is a resistance of the device R d maybe, and here is the R electrical and L electrical, and here is a transducer. Is there anything I am missing? No. And here is a current, there is I flowing. Fine. So, how will you do it? as I have already shown in that decimation problem, this can be done in two possible ways. In first, you take the electrical subsystem and the mechanical subsystem separately, write down the separate T, V, Hamiltonian and all that, and then obtain the differential equation separately. And then since you know how much is the force depending on the current here, and this also applies some kind of a back EMF, say E, always does so. Whenever there is a electrical to mechanical coupling, it will always happen. So, it also applies a back EMF, because here is something magnetic going on, there is a interaction between these two, that will apply a voltage here, which will be seen as a back EMF. So, here is a voltage that is seen by the electrical subsystem. So, the total amount of voltage applied on the electrical subsystem is E minus small e, and that on the mechanical system is F. If you want to do it as a single electromechanical system, then also you can do that, but remember in that case the F is proportional to I, and therefore, it will result in a velocity dependent potential. So, you cannot take the original Lagrangian equation that we derived, you have to take the, for the first principles we have to take the T instead of L, that is all. I have already illustrated how to do that. The sixth problem is, ever seen a seismograph by which the ground oscillation is measured? So, it is a similar kind of device. Say here it is rooted to the ground, and the whole thing is a box, a hollow box. Okay. Inside it you have a spring mass spring damper kind of arrangement. So, when this ground moves, this body cannot move instantaneously. So, their difference essentially measures, there will be a pointer like this which measures the up and down motion of the ground. I mean, this is rather crude picturization of what is actually inside. What is actually inside is far more complicated, but this gives you idea about how to do it. Now, here you have the ground motion, ground is in that case not static, there is a ground motion, say in the y direction, and then this is the k and this is the r, and here you have m, and this fellow, well, if you are considering the motion of this one, you do not need the mass, need to consider the mass of this, because the whole thing is moving up and down. So, you can see that this point is moving with that velocity. So, this point and that point are moving with a velocity, in between you have to modulate. Problem 7, the train. Suppose here is the track, here is the engine, and here are the two coaches. How are they connected? They are always connected by a spring damper arrangement. Okay. So, you have three masses m1, m2 and m3. There are two springs, let them be equal. So, k and k. There are two dampers, let them be equal, r and r. And obviously, this fellow is pulled with a velocity, with a force F, that is the engine force, force provided by the engine. So, make a model of that. They will all individually have their own degrees of freedom. in actual practice there is a limit to which these things can be compressed. In actual practice there are two hard plates which can collide with each other. So, compression is limited, but the tension is not limited, and this compression being limited is what? It is a non-holonomic constant. So, if you have a non-holonomic constant, then also the same set of differential equations have to be obtained. So, that is what you obtain those differential equations. So, that gives you reasonably good amount of practice in modeling in order to obtain first order differential equations. Now, we promise to take up specifically the electrical circuits today, where the basic law would be the Kirchhoff's law. By the way, some of you may have heard the name as Kirchhoff, right? It is not Kirchhoff, it is Kirchhoff. The guy was German, and in German all the letters are pronounced as they are. So, U is always U, Bus is Bus. So, Kirchhoff is not the right pronunciation, Kirchhoff is the right pronunciation. So, the two Kirchhoff laws, current law and the voltage law, what do they say? What do they say? If you have a loop, in the circuit, then you have the voltage law, which says that as you traverse around the loop, the total voltage is 0. Okay. Sum of the voltages as you traverse around a loop is 0. So, if you have a circuit something like this, suppose you have a circuit something like this, then what are the loops? What are the loops? Well, I can identify easily many loops. This is a loop, 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 all these are loops, and along all these the total voltage should be 0. So, that is the point number 1, that the Kirchhoff's first law, the voltage law, says that around all the loops the total voltage should be 0. So, if you can identify by names, say if I say this is 0.1, 0, 2, 3, then we can easily write down the positions of the loops. For example, this loop would be said as 0, 1, 2 loop. This loop would be 0, 2, 3 loop. By the way, there is another concept that we have to identify. These are the nodes. This is a node. This is a node. What is a node? Nodes are essentially the points which can, at least in theory, be at different voltages. So, I can see that there are 4 nodes, and these 4 nodes I have marked as 0, 1, 2, 3, and the individual elements are in between them. Clear? Fine. So, if you write it this way, then what are the possible KVL equations? For this loop, it is V 0 1 plus V 1 2 plus V 2 0 equal to 0. Now, notice I am not writing the opposite things, I am writing 0 1, not 1 0. The idea is that you have to traverse always in one direction. Which direction you choose is your business. You could as well choose the opposite direction, it will not matter, but you always have to choose a particular direction and go around it accordingly. So, similarly you can write V 0 2 plus V 2 3 plus V 3 0 is equal to 0. You can also write for this big loop, you can write V 0 1 plus V 1 3 plus V 3 2 plus V 2 0 equal to 0, right. So, so on and so forth. You can identify many loops in here, and for all that the Kirchhoff's voltage law would be applicable. What is the Kirchhoff's current law? They will be applicable to, let me draw this circuit once again. We had started with the in that Kirchhoff's current law, you have to identify the nodes 1, 2, 3, 0, and then the currents that either enter or exit each of these nodes would sum to 0, which means that the currents that are coming into this node, which are this current and this current, or the ones that are exiting this node, this current and this current, they will all sum to 0. So, you can write the KCL equations as, say, I am assuming the currents that are entering a node to be 0. Remember, that is my convention. How I take it is my business. So, I consider that the ones that are entering the node are 0. So, I will write what? No. I have not said that yet. All I have said that is that there is a direction of current here, there is a direction of current here, there is a direction of current there. All of them add to 0. All of them add to 0. It does not mean that actually they are flowing like this. They could flow like that. But when I say the I 31 plus I 21 plus I 01 equal to 0, I essentially have considered a specific sense of positivity of the currents. If the currents actually flow in the opposite direction, they will be negative. So, what? So, I can write similarly the KCL equations, that is for node 1. I can also write for node 2, I 1 2 plus I 3 2, not 2 3, 3 2 plus I 0 2 is equal to 0. Here now I can as well write the equation as the currents that are exiting the node interchangeably. So, for 3 I will write it as if they are all exiting the node. So, it will be I 3 1 plus I 3 2 plus I 3 0 equal to 0. That is all right. So, whether you assume the entering directions positive or exiting directions positive is up to you. You can easily see that if they are all negative, they will cancel off. But now, where are we? We have seen that these are the voltage equations and these are the current equations. Plenty clear that the number of equations that we have is far more than what we really need. So, something needs to be done to organize this mess. Secondly, how do you write the differential equations? In order to write the differential equation, there has to be a clue, something like differential has to be there. That clue comes from the fact that if there is an inductor in a specific line and there is a current flowing through it, then we can write the dV dt as for the sorry, this LDI dt. So, LDI dt is equal to the V. So, this gives di dt as V by L. So, here is the voltage across the inductor. Similarly, if there is a capacitor in a line, again the current is I and the voltage is say V, then it will be C dV dt is equal to I, or dV dt is equal to I by C. So, these are obviously differential equations. So, the immediate conclusion is that if in the circuit I notice that there is an inductor, then I will be able to write this equation only for that inductor, and if there is a capacitor I will be able to write this equation only for the capacitor. These are first order differential equations. So, that leads to the conclusion that for each of the inductor there will be one first order equation, for each of the capacitors there will be one first order equation. What to do about the right hand side? This could or could not be a chosen variable. So, all we need to do is to express this in terms of the variables using the Kirchhoff's laws. Okay, let us illustrate. Let us take the okay, as yet we have not organized this mess, too many equations. You might say that why not go the same way as we did in case of the Lagrangian equation or the Hamiltonian equation, use the mesh, that means the open windows. In that case all these loops are not the independent loops, only this, this and this remain the independent windows. Yes, let us do that. So, that will be the mesh current method. Let us apply that to first a very simple circuit and see the consequence. This one I am doing because this I already did for the Hamiltonian method, so that you can compare. This is E, L, C, R, and we said at that time that here is a loop which we will call Q1 and here is a loop which we will call Q2, but while writing as the Kirchhoff's laws equation I will give the I1 and I2 currents. So, the I1 is Q1 dot, I2 is Q2 dot, fine. Now, what are the nodes? Here is a node, here is a node, here is a node, here is a node. Wait, they could all logically be at different voltages, but this is trivial. Why? Because there is only one branch connected to this and going on to this, and therefore, the Kirchhoff's current law will be a trivial equation. So, we will ignore that. So, effectively there are two nodes, and whenever you use that we always assume that one of them is at the ground potential, so that we measure the voltage of the other. So, that is the standard procedure, but let us see. First let us apply the voltage law, mesh current method we said. In the first loop the voltage law will look like E minus here it is a voltage drop L di dt minus this is a voltage rise. So, instantaneous polarities. So, this is a voltage rise E minus L di 1 dt. Okay. Here it is, if this is the assumed positive polarity. So, you have to assume which is your convention of positive polarity and which is your convention of negative polarity. So, assume that this is my polarity convention. If the upper plate is positive with respect to the lower plate, I will call it the positive. So, if that is so, then this is also minus, fine. And the second equation gives V c minus I 2 r equal to 0, right. The first equation immediately gives the differential equation d I 1 dt is equal to take it to the other side E by L minus, right. So, that is first equation, no problem, done. But then this is not a differential equation. The second equation is not a differential equation. Therefore, we have made no headway in obtaining the complete state of differential equation using the mesh current method. Then I have to apply the node voltage method. I am assuming that you have learned all that in the first year. So, I am not redoing the whole concept, I am just using the method. So, then we have to apply the mesh node voltage method, because the mesh current method proved to be insufficient to obtain the complete set of differential equations. So, if you apply the node voltage method, how many nodes are there? 1, 2, 3, but these two are trivial, I will apply it here. So, for this one, if I say the node voltage method, then it will be the Kirchhoff's current law will be I 1 here, okay. I 1 here minus I 2 here, and here is minus what is this current? C, yes, C dVc dt is equal to 0, okay, which immediately gives you the differential equation dVc dt is equal to 1 by C I 1, I 1 is state variable, so it remains minus 1 by C. Now, I 2 is not, because I am now obtaining the differential equation in terms of I 1 and V c. So, I need to do something about it, but this one helps, right. So, I can see that this is equal to I 2 is equal to V c by R. So, into that is another differential equation. So, the crux of the story is that yes, it is possible to obtain the differential equation starting from the Kirchhoff's laws, but you have to apply both the Kirchhoff's laws. You cannot obtain simply by the node voltage or simply by the mesh current method, you have to apply both, clear. Just let us illustrate it with another example to get it clear. The same example that we were doing, the 3 loop example, it is a E, then an inductor, then a capacitor, then a resistor, another resistor here, and is it visible? Yes, a capacitor here. Fine. In this case, we will say here is my loop I 1, here is my loop I 2, and here is my loop I 3. Okay. So, my E, L, C 1, C 2, R 1, R 2. Quickly write the mesh current equations. Write the mesh current equations quickly. Remember, you have to go around the loops and you have to keep track of the positives and negatives. That is what is the most common mistake that people make. What I will do is, in order to not to make the errors, I will mark them 0, 1, 2 and 3, and then say the mesh current method will give V 1 2 plus V 2 0 plus V 0 1 is equal to 0. Happy? There is no problem about it. Okay. Similarly, here it is V 0 2 plus V 2 3 plus V 3 0 equal to 0. Similarly, here in loop 3 it is V 1 sorry I will write this way V 1 3 plus V 3 2 plus V 2 1 equal to 0. So, these three are the Kirchhoff's voltage law equations, as yet trivial, but I did write it this way because I know that most students make a problem in science. So, first write it this way and then substitute it. We have understood that the right way of choosing the variables would be to say that the inductor current, the current through an inductor is a variable and the voltage across a capacitor is a variable, right. Why? Because of these two, current through the inductor, voltage across capacitor, these are the minimum variables necessary. So, we will say the current through the inductor and the voltage across the capacitors are the variables. So, all these currents I have to be careful about this particular current. This is what will become a state variable, this will become a state variable, this will become state variable, but we have to be careful about what we call positive and what we call negative. Suppose this is called positive, say this direction of the current, say this direction of the voltage is positive, okay, and say this direction of the voltage is positive. So, that is my convention of positivity. Whenever it takes this value, it will be positive, else it is negative. Now, what is IL? IL is the current through the inductor. IL is I1 minus I3, fine. So, that is one thing. Then the KVL equation becomes, write the first KVL equation in terms of that. Now, write it carefully using this convention of the positives and negatives. It will become E minus L di dt. So, minus L d I1 minus I3 dt. This is positive and therefore, if you go this way it will be negative. So, minus V c equal to 0, right. V c 1, yes. Now, these negatives and positives are important. I am again insisting on that, because I know in the examinations most of you will make a trouble in that. That is why I went carefully this way. So, this is one equation. This gives a differential equation, but in terms of this, fine. Second equation becomes, it was this, this. So, we go up along the V c. So, it is V c 1 minus the drop. So, minus R, it will be I 2 minus I 3, okay, I 2 minus I 3, this one I R 2 minus I 2 R 2 is equal to 0. Oh, 1, yes. Third one, the one at the top, it will give V c 2. Now, here I am going anti-clockwise, is a rise, so I have to go this way, minus R 1, it will be I 3 minus I 2, okay, no, I 2 minus I 3, for the current sense, I 3 minus I 2 minus I 3, then yes, minus L. Now, notice the direction, this was the direction of I L, I am going this way, it is I 3 minus I 1 is flowing this way. So, either you put plus of this or minus of this. So, be careful about it. If I say, if I write minus here, it is L, what do you say, d dt of, no, if it is minus, then I 3 minus I 1. V C 2 up, going down, okay, plus minus minus, okay. So, minus, it will be a drop if the current is flowing this way. Wait, I 1 minus I 3 is the current this way. Oh yes, 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 you are right. So, this is the equation. Once you have obtained this, which are the differential equations? This is the differential equation, this is the differential equation, this is not. So, we need to apply something more to that. So, what, any problem?
No, I 3 is anti-clockwise.
No. Here's the point. We are going this way up, this way down, and this way down. So, it is I 2 minus I 3 is the current this way. No, that is right. Okay. Yes. Now, fine. So, we have written down the equations. Ultimately, we need to obtain the differential equation in terms of I L. So, just substitute it here, we get d I L dt is equal to E by L minus V C 1 by L. One equation done. Okay, from the first. Now, in order to proceed, we need to write the KVL equations, sorry, KCL equations. So, KCL equations are where are the equation? Yes. I L here, this current here, this current here, fine, let us write it. In which node should I write? Which node should I write? Let us write it here, at this node. If you write it at this node, it will be, can you see that? Yes, yes. In this node, it will be, here it is I L going into it. No. I want to write in terms of the dVdt's. So, it is going into, this is going into, and this is going into. So, you have to write it that way. So, that is minus C1 dVc dt, and this is again minus R1 dVc 1, yes, you are right. It is V, here the potential is Vc 1 and here the potential is say V 3, this point, Vc 1 minus V 3. So, R 1 Vc 1 minus V 3, no, I want the current, yes. Okay. So, this is the equation in this node. Now, I need V 3 in order to substitute this. So, yes, we can write that easily, but let us extract the differential equation first. dVc1 dt is equal to, write the rest of it in the right hand side, it will be 1 by C1 IL minus 1 by R1 C1 Vc1 minus 1 by wait a minute, is this right, plus R1 C1 V3, anything else? Yeah, done. Now, can you substitute this point? Apply KCL in node 3. What do you have? Write the KCL equation in node 3. It is V 2 minus V 3 by R 1, there is a current here. Input. So, it is, this current is minus V 3 by R 2, and the other current is this and that current would be well, this is plus, this is minus, so it is plus C2 dVc2 dt equal to 0. From there you can extract. So, just write down this equation in the proper form, so that you extract the differential equation out of it. This in the left hand side and the rest in the right hand side. dVc2 dt is equal to can write properly minus R 1 C2 Vc1 plus 1 by C2 1 by R1 plus 1 by R2 V3. Now, V3 is what? Here also we have to substitute V3, here also you have to substitute V3. V3 is what? I need to write down what is V3. So, we can extract it from here. V3, V23 which I know, and V02, no, it will be easier to extract from this equation, this one, yes. E minus Vc2 is this. So, we can extract from there. Good. So, we just substitute it here, it will be E minus Vc2. Here also E minus Vc2. Okay. Done. So, this is how you extract the differential equation. You can see that in keeping the signs correct, we had to really spend a lot of attention. In order to extract the right things, we have to find out where is that information available. It was spending a great deal of attention. And moreover, the problem is that always this assumption that the current through the inductor and the voltage across capacitor will be the minimum number of variables will not work. Why? Just imagine a circuit which is something like this. I am just replacing one of the elements in the last circuit. It was like this, sorry, it was capacitor, and this is a capacitor, this is a resistor, and here is another capacitor. What I have done? I have replaced this resistor by capacitor. Okay. At this time, I can identify a node and identify a loop like this. It is after a loop, it is not a window, it is not a mesh, but it is a loop. If you write the case KVL in this loop, what do you have? You have E, say this is C2, this is C1, this is C3. So, E minus Vc2, because this was plus, this was minus, then you come here, it is plus Vc3, this is plus, this is minus. So, minus Vc1 equal to 0. You notice that the voltages across the capacitors, these are the voltage across capacitors, they no longer remain independent. Why? Because they are related by this equation. All of them cannot be independent, because this addition, this is a externally applied voltage, this addition is 0. Therefore, these three cannot be independent. Can you see that? If it is, if these three cannot be independent, I cannot assume all the voltages across capacitors as independent state variables. So, here is the problem. Notice that? Okay. Let us give another example. Say there is a circuit something like this. I again make a small replacement. Here is the voltage source, here it was the inductor, and here it was a capacitor, that remains the same. Here it was a resistor, that remains the same. Here only I replace it by an inductor, and here also I replace it by an inductor. Suppose I have a circuit like this. See the problem. If I write this node equation, then what do I have? Suppose this is now a current source I. Imagine that this is a current source, and in that case the equation becomes I is equal to I, this is 1 2 3 0, I 1 2 plus I 1 3, right? Obviously, or I minus I 1 2 minus I 1 3 is equal to 0, whatever it is. This immediately means that these two inductor currents are not independent variables. So, if you have a circuit like this, then the inductor currents no longer remain independent variables. If you have a circuit like this, the capacitor voltages no longer remain independent variables. So, I have identified a few main problems with applying the Kirchhoff's laws in a raw way. In a raw way, what? We have simply taken the mesh current and the node voltage and proceeded to write down the differential equations. We have been able to write, but that will be true for relatively simple circuits. Even for a 3 mesh circuit, it was becoming a bit tiresome, right? So, it is not good. And secondly, if we have this kind of arrangements of the circuit, then the basic assumption fails. So, we need to have some kind of a systematic way of doing this. In the next class, we will tackle with that systematic way of doing this. Thank you very much.